So, hello everyone. My name is John O'Reilly. I'm based in Galway in the west of Ireland. As Greg said, I work remotely for a Norwegian company called Neat, and it's a pleasure to be here today in Paris talking to you. Very small bit about myself. I'm a Kotlin GDE. I've been working as a software engineer for over 30 years now, and I've been working in the Android, and the Android iOS ecosystems since 2009. So, lost the. That was it, yeah, 2 slides. This is the thing, I'll move this over. Okay, hello. So I decided I should put this up today. I really appreciate folks here coming today. I know there's kind of mixed interest. So hopefully I'll try to speak really quickly so you get to see some of the second half maybe. As the title suggests, we're going to talk today about a couple of key areas that I feel have contributed to the increasing convergence of native iOS and Android development. An emphasis on native here, by the way. First up, we'll cover some examples of how similar the Swift and Kotlin languages are. This isn't necessarily something new, but is of course an important element to this dynamic. But as useful as it is, what I think is more impactful is the very similar approaches we now have on iOS and Android for both UI development, using Swift UI and Compose, and more recently the fact that we have much the same mechanisms available for managing concurrency on both platforms. And just to also mention, somewhat in the context of both platforms using declarative UI frameworks, is I think that we've converged to a large degree on the use of MVVM, or at least a sort of a unidirectional data flow type variation of it. Lastly, not something I'm going to talk about in any detail, but I think also interesting to note how similar Android and iOS devices have become, and the closer alignment of UX patterns. So just wanted at this point to show some of the key milestones that have brought us to where we are today. Both platforms started growing in earnest around 2008, 2009. And of course, at that point, we were using Objective-C on iOS and Java on Android. These, by the way, forgot my props. These, by the way, were some of the devices we had at the time. This is the tiny, by today's standards, iPhone 3G. And this is the Android-based G1 with this sort of funky pull-out keyboard. Yeah, get it right away. And showing these here, I suppose, as well, just to sort of highlight again, the fact that devices, as mentioned, have become a lot more similar over the years, obviously, changed significantly, and have become significantly more aligned. So fast forward then to 2014, Swift is now supported on iOS, and 3 years later, Kotlin on Android. Languages, as we've mentioned, that are significantly more similar to each other than Java is to Objective-C. 2019 then was a key year for UI development on both platforms. Jetpack Compose was announced at Google I/O that year and formally released in 2021. Swift UI then was announced at WWDC and released later that year. And lastly, we saw the announcement of the new Swift 5.5 concurrency functionality at WWDC 21. So just some brief additional background and context to some of these developments before we dive into the comparisons. This was an article written in April 2019 by Jesse Wilson, talking even at that point about how Android and iOS development was converging. He was primarily basing this on similarities in the language, device and UX alignment, and also mobile team organization. But within 2 months of that article, we'd see announcements of frameworks on both platforms that would have a much bigger impact on that convergence. First off, a few weeks later, we saw the announcement of Jetpack Compose at Google I/O. And then about a month after that, Swift UI was announced at WWDC. And in terms of my own interest in this area, I had at that time, as part of Kotlin multi-platform work I was doing, been developing a native iOS application. And as someone that hadn't been opening up Xcode that frequently for a while, I always struggled to remember again how to set up storyboards and view controllers and table views and so forth. I'd seen the announcement of Jetpack Compose at Google I/O, but to be honest, it was a little abstract at that stage. I didn't really appreciate at that point what declarative UI was all about, or the impact it would have on mobile development. I was watching WWDC then, not long after that, and saw the announcement of Swift UI, which was available in Xcode beta that evening. The early hours of the morning, I had my first basic Swift UI application, and I finally appreciated what declarative UI I offered. Something down the road, I think that would be many people's experience when using Compose on Android for the first time. One interesting point worth noting here as well, I think, is the different sequence in which some of these developments became available on each platform. On iOS, we started with declarative UI and then later added structured concurrency, whereas it was the other way around for Android. And I think this has had some implications for the way existing functionality has had to evolve on both platforms. Okay, so let's dive into some of the comparisons. Firstly, the languages themselves. So I'm not going to do an exhaustive comparison of Kotlin and Swift. Rather, I'm going to use a number of examples to illustrate how they compare. I'm going to be mostly basing these on examples, on articles like this that I've seen people in the community tweet about. So John Sundell wrote this article on different ways of iterating over Swift collections, and I thought it would be interesting to see what the Kotlin equivalent would be. So if we look at the first few examples from the article, probably won't take people too long, but can folks spot which is Swift and which is Kotlin? Yeah, and if we add in the array declaration, it's a little clearer which is which. Differences in the use of parentheses, let versus val, print versus println, for example, but clearly very similar other than that. A few more from that article, and again, key thing is how, at a minimum, Swift is at least very readable to someone who knows Kotlin and vice versa, and probably wouldn't take a developer from either platform that long to figure out how to write code for the other. And lastly, from John's articles, we see some examples of iterating over maps, and I think we see even closer similarities here. Again, map variable declaration aside. Okay, lastly in this section, another article this time from Saroon about sorting Swift arrays. And again, we see the similarities. API is almost identical on initial examples with some differences in how we set up custom comparator. But again, easy to understand either approach. And we'll see some additional comparisons of the language in the next few sections where we talk about declarative UI and structured concurrency. Okay, we're getting to what I think are the more impactful similarities we have today. Firstly, the use now of declarative UI frameworks on both platforms, Swift UI on iOS and Compose on Android. So most folks here are probably somewhat familiar with either Compose or Swift UI, but just to level set somewhat. So a common way of explaining declarative UI is in terms of the what versus the how. With declarative UI, we declare what our UI should look like in a particular state, and state is very important in this context. Any changes in state cause the appropriate parts of our UI to be re-rendered or recomposed. Another interesting implication of this approach then is that it at least encourages use of MVVM on both platforms. And typically, as mentioned, unidirectional data flow type variation of it. As well as Swift UI and Compose, it's also the approach used in the likes of React and Flutter. And as we mentioned earlier, Swift UI was released in 2019 and Compose in 2021. So going to illustrate comparisons again with a few examples. So this was a tweet from Thomas Rickard about GraphQL Swift UI sample he created using the Apollo library. I'd been using Apollo in shared Kotlin multi-platform code, so I thought it would be interesting with Thomas's blessing to create a Compose and Swift UI version of that project that consumed the shared code. These are iOS and Android screenshots from the sample, and we're going to drill down and compare, for example, how a row in this list would be represented in Swift UI and Compose. So at a glance, firstly we see that Swift UI uses structs to represent UI elements like this, and whereas Compose uses Kotlin functions. But if we ignore the outer, what you might call wrapping around the UI elements, I think we see more clearly how similar these are. Some differences, of course, like HStack, VStack in Swift UI versus row column in Compose. We have async image in both Swift UI and Compose to display an image from a URL. There's text elements in both with some differences then in how styles or etc. are applied. But again, the key thing is here is how closely the concepts align and how easy it's becoming for a developer to sort of translate the UI from one platform to the other. And hearing more stories about this where some UI might be originally developed in Swift UI and then is translated into Compose or vice versa. Another example from one of the samples I have, this time illustrating the use of Canvas on both platforms. This particular sample, a little bit obscure, it makes use of what's called a chip-8 emulator in shared Kotlin multi-platform code. This was an instruction set used in the arcade games of the past, the likes of Space Invaders. The emulator code generates an array of display data as it runs its program, and we want to show that then in our application. So we're able to, as I said, use Compose in both Swift UI and Compose. Sorry, we're able to use Canvas in both Swift UI and Compose, again with very similar code used in both. Here we're iterating over that virtual display data that we're getting back from the emulator as it runs this program, and then using Canvas APIs on both platforms to update the UI. Again, small differences in the API used, but again, fundamentally the same approach. And one more example from another sample I have, this time for this Fantasy Premier League application, again using Swift UI and Compose. And again, we see the similarities in structures here, and particularly again, if we focus in on the UI elements, some differences again in the API used and how styles, padding, etc. are managed, but much the same other than that. In general, if we think of our UI as a tree of components, if we think of our tree, we're going to see closer similarities for ones like this, but with perhaps some bigger differences then when we get to screen level representation in terms of, for example, how things like navigation are managed. So speaking of navigation, there were some Swift UI changes announced this year that make the approaches to navigation and a number of other areas actually more aligned than before. going to say, gives me a chance. Sorry? Mm. Oh, wow. How have I not noticed that? Thank you. That's why it stopped. So speaking, so first up, navigation. This is a pared down example from Compose code in this People in Space sample, showing some of the key navigation parts of how navigation could be managed using nav host and then composable then for each destination. And this is what this might look like in SwiftUI now with iOS 16 updates, using navigation stack and navigation destination, which map somewhat loosely to Compose's nav host and composable. Some differences still in that Compose uses route-based or route-based approach, whereas SwiftUI maps to destinations using data type, example, the assignment type here. Different handling of start default destinations, but at least these updates, I think the approaches are certainly more closely aligned than before. Next iOS 16 update is the addition of chart support in SwiftUI. This is an example of it here on the left, along with an example in Compose using a third-party library called Qualiplot. And showing this here is a sort of a segue, I think, to an interesting point about SwiftUI and Compose ecosystems. SwiftUI Charts is provided obviously directly by Apple. There's an expectation in general that Apple will provide most of the libraries that a developer will need when developing, say, iOS apps. Whereas in Android, there's more of a tradition that many of these solutions will come from third-party offerings like this. Next up, any layout, also added in iOS 16, explained, for example, as something that enables dynamically changing the type of a layout container without destroying the state of the subview. So quite a mouthful. But then similar then, interesting to see then, relatively recent. It's similar then is a relatively recent addition to Compose, which is movable content of, and again very similar examples in the documentation for both, where it talks about how it can be used to produce a composable that moves its content between a row and a column based on a parameter. So different syntax, but quite similar and very useful capability now available on both platforms, particularly when you start looking into sort of adaptive UIs. Another small change in iOS 16, text fields that automatically grow with their content, and again, brings in line with Compose behavior. And interesting to note here the use of text field in both SwiftUI and Compose. Next up, example showing partially visible bottom sheet in SwiftUI, again added in iOS 16, and again providing capability that's also available in Compose. And yet another of these SwiftUI announcements from this year, this one in relation to applying text styles across a group of controls. Relatively small change, but again one that allows a bit closer, as I keep saying, alignment. In this example, we're applying the bold text style to all elements within the VStack in SwiftUI and the column in Compose, using provide text style and then in Compose to achieve the same purpose as that font weight view modifier in SwiftUI. Semantics a little different, but again, very similar approach. One last example showing swipe to refresh functionality in SwiftUI and Compose, with the latter actually provided, by the way, by Compose's accompanist library. Just to also point out in the previous text style example, a slightly different approach for applying behavior like this. SwiftUI uses what are called view modifiers, the refreshable here, for example, whereas Compose tends to sort of wrap code to apply the behavior. Interesting to note here that we can also use declarative UI frameworks for watch devices. This Compose for Wear example on the left was contributed to the People in Space sample, and on the right we see a watchOS version based on the use of SwiftUI and contributed also to the same project. Again, very similar approaches used in both. Lastly in this section, I thought it was interesting to point out that not only do we now have support for widgets on both platforms, but we can again use the same declarative UI approach for developing them. Okay, next up, concurrency. And more specifically, we're talking about the structured concurrency functionality that we now have available on both platforms. This is a really powerful capability that allows us to write async code in a way that's easy to read, and also allows a more deterministic structured approach to error handling and cancellation, for example. Key enabler of this is the ability to have code that can be suspended at particular points and resumed later. And as we'll see in a moment, SwiftUI supports these capabilities through the likes of tasks, async functions, and async sequence, and Kotlin through coroutines, suspend functions, and flow. This approach, for example, allows executing async functions both sequentially and in parallel. And we're going to show examples of both shortly, along with the examples then of the use of async sequence and flow. And a very important aspect of this is how invocation of code like this can be tied into our UI lifecycle, thus allowing, for example, automatic cancellation when the UI is no longer shown. Just to also mention at this point that the new Swift concurrency capabilities we're talking about here were included in the Swift 5.5 that was announced at WWDC last year. So firstly, let's look at examples of executing async functions sequentially, using slightly adapted version of examples from Paul Hudson's excellent series of articles on Swift concurrency. Here we have 3 Swift async functions, fetch weather history, calculate average temp, and upload, which we're invoking sequentially from process weather, which itself is an async function. Some of these functions could, for example, make a remote API request and have to wait for the response. And this is what the Kotlin equivalent would look like. We see here the use of suspend keyword in Kotlin versus async in Swift. Again, both denoting a function which suspension can occur. And also the fact that we explicitly use a wait in Swift, where suspend functions can be called directly in the appropriate context in Kotlin. Looking then at some examples of how we can invoke async code like this, again using examples, Paul's examples as a basis. It can be invoked from a main function as shown here, marked again as async in Swift and suspend in Kotlin. We can also create a task in Swift, and similarly in Kotlin create a coroutine from which it can be invoked. And where things get interesting then, I think, is how this can be tied into our UI lifecycle, along importantly then with automatic cancellation, as mentioned before, when the UI is no longer shown. We use the task view modifier in Swift UI for this, and can use, for example, launch, effect, and compose. And we'll see another example of this later. Also interesting to note, I think, that we can change this behavior as well on both platforms, such that code will be invoked when particular key changes. Whereas the previous example shows how we can evoke async functions sequentially, Donnie's article about use of async let, an associated example shows how to invoke tasks concurrently. This is again a slightly modified version from the sample, and shows how we can kick off a number of tasks that run in parallel and wait for them to complete. And we'll see this in a bit more detail in the next slides. And again, this is the Kotlin equivalent. And if we break it down a bit more, we again see the use of async in Swift and suspend in Kotlin. Very similar mechanism then for invoking these async functions in parallel, using async let in Swift and async coroutine builder in Kotlin, and then waiting for them to complete, using a wait in Swift and a wait all in Kotlin. In this case, we're going to load a list of movies, user info, and wait for them to finish, and those requests, as I said, will execute in parallel. Finally, we kick off a number of other async tasks that execute in parallel, and again, wait for them to complete. The other major component of the new Swift concurrency functionality is async sequence that allows asynchronous iteration over a stream of values. And this is something that maps very closely to a Kotlin flow. Shown on the left here are basic examples adapted again from Paul Hudson's articles of the use of async sequence in Swift. And I've added some similar examples of the use of flow in Kotlin. We use for await in Swift to iterate over the values, and use collect in Kotlin to do the same thing. And then also a few examples of some of the operators supported. Firstly, using map to convert each value to its uppercase value, and then iterating over the result. And then filter, for example, to filter on a particular string, again in a very similar manner. So as I was preparing this section of the talk, and in particular looking at ways in which Swift async sequence operators compare to those supported by Kotlin Flow, I read a few articles like this, talking about aspects of the Swift combined framework that were still missing from async sequence. At that time, there was still a gap that meant that in many cases, people still needed to use combine, or libraries like async extensions here that mimic some of the functionality it provided. So I was, of course, interested to see the Swift async algorithms package announced. And with this, we now effectively have even closer mapping between the capabilities of Swift async sequence and Kotlin flows and the operators they support. And this is a few examples of using some of those new operators included in the async algorithms package, along with their Kotlin equivalent. Using new async method provided by the package to convert a Swift array to an async sequence, with asFlow being used in Kotlin to achieve the same purpose. And as before, we use for await in Swift and collect in Kotlin. Showing example firstly of merge. And then zip here, and several other operators available in common now as well. So just to finish this section, I want to show one other example of how we're talking about very similar concepts on both platforms, in many cases using the same vocabulary. I'd watched the session at the bottom right at Kotlin Conf in 2019, where they talked about how cancellation of coroutines needs to be cooperative. Thought it was interesting then to see the structured concurrency talk at WWDC 21 talking about the same concepts, talking about cooperative cancellation of tasks in the Swift case. Okay, going to talk very briefly about Kotlin multi-platformers. It's something that I think nicely complements some of the developments we'll be discussing here, and again in the context of developing native applications and in relation to sharing non-UI code. Subtitle here, obviously not the official one, but phrasing like this perhaps to emphasize where this potentially fits in. And bringing up Kotlin multi-platform here as well, as we'll see a small example of in a while of how some of the similarities we've been discussing here make the consumption of shared code, including async-related code, pretty seamless in Swift. And a key component in Kotlin multi-platform that's of interest to us here is Kotlin native. It provides capability to compile Kotlin code natively using, for example, LLVM on iOS. Typically, a framework is created which can be consumed directly in Xcode. And very importantly, we can access native APIs directly from the shared code if needed. The last point here is something I've been doing in a few samples, which is a nice capability now to build shared code as a Swift package and add that to an Xcode project like any other library. Now just to show here, showing here how Kotlin and Swift types are mapped to each other when using Kotlin on a platform like this. I'm not going to go through these in any detail, but just to give a flavor. We'll also see some of these in a number of examples in the talk. And the previous slide was also somewhat of a segue to mention a number of other developments around the use of KSP and Kotlin compiler plugins for generating code that provides another way of providing necessary mappings between Kotlin and Swift when using Kotlin multi-platform. Thaddeus gave a really nice talk about this in Kotlin DroidCon New York a few months ago. And TouchLab, if you're involved in Kotlin multi-platform at all, you're probably very familiar with TouchLab. But TouchLab are in process of building out some really nice, interesting tooling that will provide richer interop between Swift and Kotlin. And we'll also talk about another library shortly that also takes this same approach. Okay, we're going to finish up with a few examples that illustrate again how some of these areas we've been discussing. This is based on another example I have in GitHub called Bike Share. That sample includes broader functionality, but for illustration purposes here, we're going to focus in on sharing showing a list of what are called bike stations for a particular bike network. In this case, one for the bike sharing network here in Paris. I think the one at the top is relatively close to here. So this is, again, the high-level architecture, what this might look like for an application like this. We're building native iOS and Android apps using Xcode for iOS and using Swift Android Studio for Android, using Swift UI on iOS and Compose on Android and MVVM on both. We then, in this example, have a shared Kotlin repository which we're consuming in both platforms. And then this is an excerpt from the shared repository, and we're going to use this example. It polls for info for a particular bike network and exposes that as a Kotlin flow, something we'll use directly in our Android client, but we'll map to an async sequence in our Swift iOS client. And by the way, we're mapping from that flow to an async sequence using the really nice KMP native coroutines library that I'd strongly recommend any folks working on Kotlin multi-platform to take a look at. It supports new Swift 5.5 concurrency capabilities along with a number of other frameworks. So firstly, this is what a view model might look like for this example. Typically, its purpose is as a container of observable state, changes to which will then cause our UI to be re-rendered, and as a sort of a conduit for actions we're taking from the UI that will typically cause that state to be updated. Also can be used for transforming state we get from other parts of the code to something more suitable for the UI, though not doing that in this basic example. The pattern here for iOS I think is pretty common, using observable object protocol and along with a published property wrapper. On Android we're using AC view model and also using Compose's mutable state of here to represent the observable state we're exposing from the view model. Not too important in this context, but common also to use state flow here as well as map to a specific UI state as mentioned. And on iOS, we have a poll network updates async function, which uses the new for-await mechanism of Swift, along with use of the KMP native coroutines library that maps the Kotlin flow I mentioned in the previous slide to the Swift async sequence. On Android, we're doing something quite similar, in this case consuming the flow directly, and again using Kotlin flow collect instead of that for-await in Swift. On both platforms, we're also triggering, and when we get new data, update of some state that will cause Swift UI and Compose to re-render the appropriate parts of the UI. And this is what some of the Swift UI and Compose code looks like in this example. Again, we're using a Swift struct for Swift UI and a Kotlin function for Compose, using list in one and lazy column in the other to iterate over the list of stations coming from our view model in both cases. We use the task view modifier in Swift UI to invoke the poll network updates async function, and use launched effect and Compose to effectively do the same thing on Android. And important again to note how that these will automatically get cancelled when our view disappears, and that cancellation will get propagated to the shared code in both cases. Before we show the Swift UI and Compose code for the rows themselves, just a quick recap on what we're trying to show here. We have a row with a tinted image representing how many bikes are available, and then a column containing the name of the station and availability info. And this is what the Swift UI code looks like for this. A lot to unpack here. We'll show a Compose equivalent next, and then show a trimmed down version side by side to illustrate the comparisons. But here we can hopefully see general structure with the image showing the tinted icon, color based on the number of free bikes. And then Swift UI, HStack, VStack elements. And this, by the way, is a sample from GitHub if people would like to look through this in more detail at a later point. And this is the Compose equivalent. Don't worry again about the details too much. As I said, we'll show a clear comparisons of the side by side, but it's very much the same structure as Swift UI. And this is the pared down version shown side by side. And again, hopefully we can see how similar the UI elements map very closely to each other. Even closer here than the previous example, I think. H stack to row, V stack to column, image, spacer, and text elements in both. This is giving me a chance to get some water. So yeah, H stack to row, V stack to column, image, spacer, and text elements in both, with some API differences and some differences, as mentioned before, in how styles and padding, etc., are applied. In the previous slide, I took out the tinting code just to allow clear side-by-side comparison, but just showing that explicitly here, and again, something that we've done in a quite similar manner on both platforms. Okay, next example illustrates use of combining multiple Swift async sequences in an iOS app, one of which, in fact, is mapped to a Kotlin flow. The first one representing list of players. This one, as mentioned, mapped to a Kotlin flow using that KMP native coroutines library mentioned earlier. The other then representing a search query, and we're using then combine latest operator to combine them. And I think this nicely illustrates, again, how seamless the consumption of Kotlin flow in Swift can be. One last example, similar to the previous one, this time from the GraphQL confetti sample that displays conference information. This is a project, by the way, that Martin and Benoit here are also working on. And we can see here, firstly, the Android view model, where we use combine to create a mutable UI state based on flows from a repository coming in from our shared KMM code. And then very similar code in our iOS view model using Swift async sequence combine latest, where we used combine on Android. And some of the async sequences we're combining here, again, are mapped under the hood to the same flows that from the Kotlin repository. Okay, so that was somewhat of a whirlwind tour of some of the key areas I think are contributing to the increasing convergence of native iOS and Android development. And just to recap, there are, of course, many different permutations in terms of how mobile teams are organized, depending on the company, the size of the project, and so forth. But at least now I think we have more possibilities for people working on both platforms and becoming more general mobile developers. We've seen similarities in the languages, but even more impactful and important is the common approaches we now have for both UI development and concurrency on iOS and Android. And complementing that, I think, is the possibility of using Kotlin multi-platform for sharing some parts of the boring non-UI code on both platforms. Thank you.